Hi, we're going to talk about Apple MacBook Pros, recent model ones, and how there's a potential design issue in them that's causing these failed connectors here, and it's a real problem compared with the older design MacBook Pros. Now, Lewis Rossman over at Rossman Group, subscribe, I'll link it in down below, I'll link in both the videos in Lewis's channel. Lewis is great. He does Apple repair videos and business advice and no bullshit commentary. Love it. Anyway, he did this video about these botches in the design of the recent, I believe from 2016 MacBook Pros onwards. The previous ones didn't have the same issue, or we'll get into the technical details because the devil's always in the detail here. So we're going to have a look. Is this a design oversight? Is it bad design? Who at Apple, which engineer at Apple is responsible, if any? Because it's a real interesting question. We might dive down the rabbit hole a bit here. So take it away, Lewis.
Another Apple design flaw. Many of the design flaws that I've discussed in Apple products affect products from 2008, 9, 10, 11, 12, 13, 15. However, today we're going to get to a flaw that's affecting machines from 2016, 17, and 18. I want it to be clear when I say this that it's not just pure hatred for Apple products that I do this. It's because I hope that the consumers of Apple products, when they realize that they're designed in this way, ask the company, can you do better? As a $1 trillion company that sells $3,000 machines, can you do just a little bit better than something we would expect from a first-year intern? So today we're going to be going over a very common problem on the 13 and 15-inch MacBook Pros with USB-C ports, which is no image. I want to go over the design flaw that causes no image, how it manifests itself, what it looks like, and why this is a really bad design in contrast to older machines. With many of the design flaws that I discuss here, I'm talking about things like this cap failing or this thing being placed in the wrong place and stuff where you could, okay, it's kind of understandable that this mistake could occur, and it sucks that you didn't fix it after a few years, but understandable to some extent. Here, this is just objectively terrible in a way that I would like to show you. So
is it objectively terrible? Well, we're going to get into it. Let's check it out. Link in Lewis's video down. You can watch it for yourself. There's another video here, which I'll link it as well, which is one of Lewis's cohorts, and it actually
so what we have here is a 1707 that sustained liquid damage, and as most of the time they do when they get liquid damage, just because of the way the liquid gets into the machine.
And here's the connector.
It destroys this connector right here.
This is the LCD connector that goes from the motherboard over to the LCD
So this connector
module.
Is for
Ouch, look
the
at
screen.
that. That's nasty. You can see the carbonization between the pins in there.
And what you're looking at here,
that's terrible,
is this big pin is what carries the backlight voltage to the screen.
And that's about 50
so the biggest. So this is the biggest voltage that you're going to have, and this pin right here goes to, on this machine, luckily it goes to a muxing circuit that changes between the integrated GPU and the discrete GPU.
Okay, so the problem here is that the backlight voltage pin on the LCD connector is right next to a data line, which is going to either, depends on the model, either goes to a mux chip or goes directly to the CPU. And if there's any sort of arcing or any sort of water gets in there and then bridges out between those two pins, and I'll do a demonstration shortly, stick around for that, that can cause a low impedance or any sort of carbonization, for want of a better term, between the pins in the connector, causes that low impedance. Generally, the backlight power supplies are reasonably capable. They're capable of at least, a handful of watts. And then if you've got a low impedance over to a data pin, a lower voltage data pin, that's going to ruin your day. Current can flow into the data pin, and not only in the data pin, but through the protection diodes as well. I've done a separate video on that, and that can just take out all sorts of stuff. So it can either take out your mux chip or the CPU. If you've got the model where it takes out the CPU, it's ridiculously expensive. Of course, Apple don't sell any of the parts, so you've got to scrap them from existing boards. Apparently you can buy them, but I think Lewis says they're like, $180 or something like that, and then you're not even guaranteed that they're going to work. Did they scrap them properly? All that sort of jazz. So yeah, really nasty problem. And the older ones didn't have this sort of, well, they didn't have the same issue that the later MacBooks. Now, I've got the open board view software written by Paul Daniels. I'll link it in down below. It's brilliant software. So we can have a look. This is the MacBook Pro board. And if we have a look at the connector up here, and these are the two pins we're talking about. Why they've labeled them 43 and 1 like this, I don't know. We'll go into that shortly. But anyway, here, this is where the fault occurs. Pin 43, as you can see, is the LCD backlight voltage. Lewis says that's about 52 volts, but that can vary between the models. And then pin number 1 here is this auxiliary data pin, just goes off to either a MUX or a CPU or whatever. So there's no ground in between them. There's a little bit of spacing because it's physically a much bigger connector. And we can actually have a look. And here's the actual connector. I think it's a Novastack one. It might be an equivalent. There might be various equivalent ones, but you can see it's physically like a larger pin in there, and that has the backlight voltage. Normally you might just use that as a big ground pin or something like that, but Apple decided to use the backlight. There's nothing wrong with that because it is a larger physical contact pin, so they might have needed it for the higher current. So physically it's one of these just flat flex board interface connectors, and there's nothing wrong with the choice of that connector. In fact, if we go over here to the spec sheet, the voltage rating of the connector is actually 60 volts AC or DC per contact. It's basically a 60 volt rated connector. So the design engineers of Apple, they've chosen the right connector. It's rated properly. No worries. So the first thing we're going to take a look at is conductor spacing, because the higher voltage you go, the more distance or creepage distance and clearance you've got to have between your pads. Now, I've mentioned clearance and creepage before, but say clearance in PCB terms, it means an air gap. So if you've got two physical pins, or two wires or whatever with physical air gap between them, that's the electrical clearance. That's different to what's called creepage, which is, let's say this is your PCB here, you got one trace and you got another trace on top of the PCB next to it, just imagine it there, then the voltage can creep along the board and from one trace to the other, can follow the contours. Or if you've got a connector like this, for example, this would be a matter of creepage, not clearance. So the distance between the pins in here actually goes along the connector, and if they've got little ridges in there, it follows it. If they've got little bumps, it'll follow it. That's what we're talking about, the creepage distance between those pins. But we've already seen this connector is rated for a nominal 60 volts DC AC, so it's fine. We don't even have to get out the Saturn PCB calculator here and actually calculate it, but let's just look at some typical numbers. From 51 volts to 100 volts, they only specify ranges. You know, there might be some other calculators on the market that you can type in the actual voltage value, but it's a bit, how you doing? So if we look at a bare PCB with just bare copper traces on here, on the surface like this, for 51 to 100 volts, to have a safe creepage distance between them, or conductor spacing, you need to have 0.6 millimeters. So that's actually not a huge amount. That's why this connector can have that 60 volt rating with those small pins. And a lot of people don't realize that that'll change with elevation as well. So if you go and use your MacBook Pro on the top of a mountain over here, you've got to use it on the top of a 3,000 meter mountain. But if you did that, then you would, how high is Everest? Anyway, if you did use it above that, technically you have to go to 1.5 millimeter conductor spacing. And once again, there might be some how you doing formulas out there for the height of things like that. Anyway, you see, we're already starting to go down the rabbit hole of PCB design here, and clearance, conductor spacing, and creepage. But it'll be different if you have solder mask on the PCB. It's only 0.13 millimeters. Once you add solder mask. Solder mask is an excellent insulator. It allows you to get closer conductor spacings, but of course when you've got a connector, then you've got the exposed pads, of course. But if you can get the solder mask between the pins, which you should to prevent shorting between the pins during reflow or hand soldering, but then you get much better much tighter conductor spacing. But all bets are off in the case of the MacBook Pro, where you get liquid damage, and I'll do a demo in a minute, stick around, where water can get between your pins, and then the solder mask isn't going to save you in that particular case. And by the way, if you actually have it buried inside an inner layer of a PCB, then that's the best, really. It's better than solder mask, only 0.1 millimeters compared to the 0.13 there. Anyway, conductor spacing is fine. So Apple have done their job in terms of choosing the right connector and conductor spacing on the PCB. That'll all be fine, no worries. But let's go do a little demo to see what happens if you actually get liquid damage on your PCB. Let's see what can happen at a lousy 50 volts. This could be interesting. All right, so what I'm going to do here is a little demonstration. I'm going to get a 52 volt power supply. I got 32 volts in series with 20 volts here, both set to 2 amps. And I'm going to connect that down to a breadboard down here, just 2 adjacent traces like this. So this will like simulate the 52 volt rail and ground or some other data line that it can go to. And we're going to pour various things on it and see what happens. Okay, I've got some water here. It's just been in a bottle that's, I don't know, been sitting on the lab shelf for a while. So let's put that on there, see what's going to happen. Anything? I think we can see some bubblies. See some bubbling action. Of course, the gap between the traces, I think, is probably slightly larger than what's on the connector. I haven't actually measured it. Yeah, you can see it's starting to react. This is just plain old water that I've had lying around. Doesn't include any gunk or anything like that in it. It's not coffee or some other liquid. Of course, this is what would happen if you have a relatively high power source inside a product like this, and you put liquid in there, then, and if there's exposed contacts, it's not going to suddenly just arc over and carbonize everything, but you can see that it's certainly doing. Hey, it's changing color. I think we're getting some sort of, I don't know, carbonization. Is that the correct word between the traces? You can see it's getting really dark. You can see it will slowly deliver power into there and then break it down, and once it carbonized, for want of a better word, between the traces, gets lower and lower impedance, so it can dump more power into that trace. That's getting really quite black now. It's not looking good, is it? Remember, this is only 52 volts. Sure, it's coming from a fairly high, heavy-duty power supply. In fact, you can see the power it's delivering there. Not particularly high power at all, and a backlight driver can easily deliver that sort of current, right? So we're not talking high powers here. And of course, if this was a solder mask board, then of course it would have to get through the solder mask first. So the solder mask is an excellent insulator, and really, in theory, the water should just, plain water shouldn't do anything to the solder mask. It should just sit there and pool and not do anything at all. But eventually it might break down the solder mask. There's always contaminants in the water. It's never going to be pure water. It's picking up all sorts of gunk as it's going inside. But of course you would get this between 2 pins of a connector, and they will of course be exposed. The solder mask only goes up to the pads, but then between the pads and then inside the connector itself, which is what seems to be happening inside the Apple, the water gets inside the connector and then just forms a creepage path across there, and it just breaks down and starts to become more and more conductive, and it pumps more and more power into there, and it can accelerate and get worse, and yeah, that's pretty ugly. All right, I've given that like a couple of minutes. Of course, you might leave it in there for weeks, a month or whatever, inside your product. So what I'm going to do is just blow that away. I won't brush it. You can really see the carbonization or something between the traces. It's still drawing 8 milliamps. Wow, check that. You can see the smoke coming off there now. Remember, 52 volts, it's just still drawing 13 milliamps. Like we're talking 600 milliwatts, half a watt. It's not much. Does not like that at all. It's just completely broken down. Ooh, starting to get a bit smelly. Don't want to set the fire alarm off. I'll call it quits there. Damn, I didn't start recording. What I've done here is another test because I thought it was oxidization on the existing traces on the board, and I just cleaned it with steel wool, cleaned it all up so there was nothing on the board, so it was just 2 pure copper traces on there. I just poured the water on like seconds ago, and it instantly started to bubble up like this, perhaps more than what it did last time. So that's fascinating. So we've got some sort of electrolysis happening here, and between, you know, 2 brightly polished pure copper traces on there with water that just came from the bottle. Sure, it's been sitting on my shelf for a while, but it is like, you know, the regular spring water. And once again, I'm getting that, 18, 19 milliamps or whatever. So it's basically in the order of a watt, pretty much. So let's blow that away. You can see one of the traces is really getting green now. Hang on, let me show you. Yep, look at that. Wow, we've got electrolysis happening there. You can see it. You can still see it bubbling and smoking. That is really quite something. Just tarnishing away completely. Love it. Okay, one more test. I'm just curious to know what happens if I increase the gap in there. So I've pulled off the inner copper trace there. So exactly the same water as I had before. Let's go. Let's see if that does anything. Oops, I'm an idiot. Didn't turn the power on. Dole. There we go. Yep, 18 milliamps. Yep. So that's interesting. Even if you increase the spacing like that, it's not really going to help you. Maybe the Apple engineers weren't at fault. It's just the nature of having a high voltage, reasonable current, reasonable power capability power supply, and you add liquid, it's going to ruin your day. I mean, there's going to be a point at, at some physical separation distance, but we've got quite a large separation in there. Like if I was the layout person doing that board and I wanted to add separation in there, it certainly wouldn't be any more than that. But we are drawing significantly less current than before. We're drawing about 7 milliamps this time. So there is a function of the distance in there, but still, I mean, that's like within seconds. That just started reacting and it's all corroded. You can see, yep, you can see that positive terminal over there. It's not a happy camper. So, yeah, that's interesting. So as you can see, there may not be much you can actually do in terms of conductor spacing and creepage distance when you've got liquid damage inside your product like this. So does that mean that there's nothing the Apple designers could have done? Well, no, that's not really the case. They could have taken various measures to not necessarily prevent this, but to help mitigate the problem when you get water ingress. Is it their fault or not? I don't know. That's still up in the air. By the way, this board view software is just fantastic, and this is the open version. There's also a pro version as well. No wonder Lewis can repair these Apple products quickly when you've got this and you can cross-correlate pins with the schematic and everything. It's just gold. It really is. Fantastic. Hats off to Paul Daniels. So did they goof up by having the high voltage pin next to the data pin like this? Well, yes and no, right? Your average designer might have come along and said, well, okay, let's just leave out a couple of pins spacing to get extra creepage distance, extra clearance. And that would be like standard practice. But as we've seen, that may not have been enough to actually do the business here. You still might have got arcing across here. So really, what you needed to do is to ensure that none of your other chips blow up. So that's fault mitigation in another aspect of design that you may or may not consider. And I don't necessarily blame Apple for missing that. Do you design your products to be tolerant to water ingress like this? Do you have them fail safe, for example? How would you make this fail safe? Well, this high voltage pin here, you could still have it right next to this pin, or maybe one over this data pin, but then you maybe could have made pin 1 a ground pin and then maybe you would have ground guard traces around here. You might even have exposed traces. I've seen this. This is quite common in very low current designs. We've seen it in, Keithley electrometers and stuff like that, where you'll leave an exposed guard trace around there that prevents the leakage from a particular pin, in this case due to either moisture or water ingress on the surface of the PCB, is then shunted to ground instead of to a sensitive mux chip or a CPU that can just have the magic smoke released when it gets low enough impedance to go across. So, really, and you might have had room in there to actually put some guard traces in there, but really I would have left a pin here and made that one ground. That just would have been, good design practice if you had thought of this problem, water ingress problem, and you were trying to mitigate any potential failures of other devices in your product. And that's not necessarily that kind of standard practice inside products. It's always a trade-off. How far do you go to try and prevent these sorts of issues? So if you had a big guard trace right around, going through this pin and right around there, and as I said, once it gets under the solder mask, it's pretty fine, but it's on the connector that you've got to worry about, and it's on the connector where we've seen this horrible damage like this. It's just carbonized that completely and destroyed any chip that this was connected to, either directly or in other things via the protection diodes built in the chip. And it's just, it's nasty. So if that pin was ground and then the others were all data, maybe, this wouldn't be a problem. Sure, it might short out your backlight power supply, but then you could have like a poly switch in your backlight power supply or some other fuse that's much easier to replace. But Apple don't necessarily design their products to be like component level traced and replaced. They do major board swaps and things like that, and that's one of the criticisms of Apple and other companies. Apple aren't the only ones that do this, and you've got to ask, well, if Apple do know about this problem, and sure enough, if they missed it, that would be fair. Missed it in the design process, fair enough. But what happens if they then knew about it? They do a new revision of the board. You would upgrade that to fix the problem. Surely you would. Any competent engineer would look at that and go, oh yeah, that's a problem. Oops, sorry, we'll fix it in the next revision. But Apple seemed to have gone backwards in this respect because the older designs actually did shunt it to ground, and I think it blew a fuse or whatever, and it was much easier to fix than replacing a big expensive BGA chip. So yeah, oops. And this leads me to a comment on Lewis's video. This is from an older video where they talked about this. And this person, Rainy Days, I think where they can see where the error arose in this case. Here we go. No single design engineer is responsible for the design from start to finish in a large corporation. That's very true, especially in terms of something so complex like a MacBook Pro. There's no way only just one person did the schematic and the layout and everything else. You've got at least one person doing the schematic. The schematic might have even been divided up. You've likely only got one person doing the PCB layout, because cooperative PCB layout, it's great in theory, doesn't really work that well in practice, but it's possible. But it's most likely that, that MacBook board that we've seen, not particularly a complex layout. One design engineer can easily do that, and it's better if you have the one design engineer do it. So they might have had a PCB layout person, but that PCB layout person might have had absolutely no visibility into the schematic side of things. Anyway, let's continue. The error started with the CAD librarian, responsible for drawing schematic symbols for new parts and maintaining the library, who incorrectly labeled pins 1 and 43 to be far apart numerically when physically they are close together. Now, this is interesting because if we have a look at the connector here, this is actually from the Apple schematic, and it's actually drawn. There's two ways to draw a schematic symbol like this. One is as they've done here, a physical representation of the connector, and you can see the backlight power is up the top here, and they physically show that as a separate pin. There's a box around here showing that these are all signal pins, and this is a physically separate power pin. And of course, that's what you see on the connector. That's one big larger tab pin. So they've actually, I don't see any fault whatsoever from the librarian point of view who would have drawn this schematic symbol. Now you could argue that why did they number it? Pin 1 and 43 up here. Well, it might be understandable because you might start labeling the signal pins first, and well, is that a thing? I don't know. They don't show the other one down the bottom, which is interesting. So maybe there's a bit of inconsistency, that other large pin down the bottom. So maybe there's a bit of inconsistency there in terms of drawing the schematic, but that's not where this problem originated. So I don't put any fault on the librarian in this case, even if it is a pin number like this. The person laying this out, the pins actually, even though the pin numbers are there, they've physically put it next to that. And any competent design engineer, especially ones familiar with the connectors in these types of products, you'd have to be when you're designing these types of products, they would have gone, oh yeah, that's probably the larger tab at the top of the connector, and you've worked on other designs and you've got physical examples in your hand, and like, yeah, it's like, I can't see any error happening there. The person who drew this schematic knew that that backlight pin was close to this auxiliary power pin, but they might have had, or they may have had the decision of buying the connector. They certainly would have had visibility. This part number up here would have been mapped. They could have gone and checked out the data sheet in their Apple's internal library systems. Almost certainly would have linked to a data sheet for that particular product. They'd linked to the 3D model and a photo, and everything should be linked together in their system. If it's not, I'd be very surprised. But they should have, the person laying out this schematic should have known that that pin was physically close to there. So that if you could blame anyone, it's the person who did the schematic, knowing they would have known that pin was physically close. So that's the first goof. You probably should have said, well, let's skip the pin down there. Because look, we've got lots of ground pins down here, tons of them. You don't need that many ground pins to, in this particular case, they're twisted pairs. So it's not like they're getting shielded in between the individual ones or in the individual pins or anything like that. So really, they could have shifted all that down and it wouldn't have, it wouldn't have mattered. You could have got at least pin 1 and pin 2 there as ground so that you could have a guard shield around it. But obviously, they weren't in that mindset when they were designing this. So I don't think that's a valid criticism. A completely different mindset, what the librarian had. The librarian is probably following the company standard. They probably would have had something like, oh, connectors must be physically similar to what they look like, rather than just numbering them 1 through 50 or whatever, and then not having a physical representation, just one big row like this, and not even having 2 sides separated. So I don't think the librarian was at fault there. When this is passed on to the layout engineer, person responsible for actually routing the design on the physical board, he routes the design blindly and does not catch the error because he does not know or really care about how the circuit functions. That can be very true. There's nothing that says a PCB layout person has to be, well, they have to have electrical knowledge, okay, but they're not necessarily a design engineer. I've worked with excellent PCB layout people way in the past, and in fact this was a carry-on. They were originally CAD engineers. They were AutoCAD, and then in the early days of CAD they'd come over and they'd be laying out PCBs without really much electrical knowledge. It's more important these days. You've got to know about, impedance control and twisted pairs and termination, loop area and star grounding, and there's tons of stuff you have to know as a PCB designer. So I'm not necessarily sure the PCB layout person would route it that blindly, but I wouldn't blame them for not capturing that problem. And I think if you're going to blame anyone here, it would probably be the schematic designer, which is more of the main product designer, because you can say PCB design is just more, I'm a former professional PCB designer myself, and I hate this term, but grunt work, right? Laying out the board is kind of, right? It's the bigger picture, actually designing the schematic, designing the product, the overall look and feel and the physical form factors and how it all goes together and the thermals and the whole, things like that. So the higher level design engineers, they were really responsible for ensuring that those pins didn't have a guard ground between them, for example. Or that the backlight wasn't fused. I haven't looked at the rest of the schematic. Is the backlight fused or whatever? If it's not and it didn't have a ground path going to ground, then yeah. When the board goes through testing, nothing is ever caught since nobody has the foresight to purposely try to short a design during testing. And that can be quite right. But when you're designing, and you've been designing, Apple have been designing consumer products for a long time, they should know about water ingress, especially MacBook computers, right? People pour stuff on the keyboard, it gets in there and ruin your day. It's a common failure mode, but is it the mindset of the company, in this particular case, Apple, that, look, we don't care about if users dumb enough to spill water in them, hey, we'll sell them a repair service where we'll replace the whole motherboard, replace the whole lot, or we'll just sell them a new one. And that's, so Apple have some blame there from that point of view. But do you blame the design engineers for not mitigating against water ingress like this? Because it's not just the 52 volt supply. You could actually get electrolysis happening on other rails as well, and that could ruin your day. So really, how far do you go to ensure that that backlight wasn't going to go into another chip? With hindsight, it seems obvious. Yeah, don't put it right next to a 52 volt rail right next to a data pin. That's just, asking for trouble without having some sort of ground guard trace mitigation in there to shunt that power into ground instead of it going into your big BGA processor or whatever. So with hindsight, it's obvious, but do you blame them? Yeah, it's hard, right? But once they know about this problem, if they don't fix it, then that's a problem. Ultimately, this is a flaw due to a misunderstanding, mismanagement between multiple engineers with different functions. This would never happen in a smaller company where the design is owned by one person from start to fab. So Apple, being rich and large, actually works against them because all the engineers that work on the board need to have the exact same design philosophy, or at least adhere to the same standards. This is basically true. It's, when you subdivide your tasks up, everyone kind of, it's common just to wipe your hands, throw it over the wall, so to speak. Oh, finish the schematic, job done. throw it over the cubicle wall to the layout engineer, and then they do the layout. Then they throw it over the wall to the production engineers, who then have to get it assembled and built and tested and all that sort of jazz. So there is that silo aspect to a large product design, but like anyone in the chain here could have seen this potentially, and then did they speak up? Maybe they didn't say, hey, I think this is a problem, or hey, I'm hearing on the forums that these notebooks are failing due to water ingress, and it's always this line here and it's causing a problem. Maybe we should fix that on the next revision, or maybe we should be careful on the next revision. But then maybe they're rotating through design engineers, so the 2012 MacBook Pro design team may not have been the same as the 2016 MacBook Pro design team, or one person left, or it's not documented, or there's no company culture at the engineering level to actually look at this sort of problem and go, hey, okay, what happens if water ingress? Water ingress is one of the big failure. You can do failure mode analysis on these things, and you could argue that they certainly should on a high volume, expensive consumer, big profile consumer product like this. A common fault everyone knows is spilling water and coffee and whatnot on your keyboard. If that gets in, what happens? But hey, they could have tested this and looked around and went, hey, it's not a problem. Like I said, don't necessarily blame them for missing this, but once they know, should certainly fix it. This flaw is still, of course, unacceptable and can be remedied with better communication and a set of internal design philosophy standards. And that's certainly true. You can implement a failure analysis on these things where you can look at a design, and in fact, you could have somebody devoted to this or a team devoted to this once you've designed your first prototype of your product. Right, how do we make this thing fail? Do they care about that? Or do they simply blame the customer for getting water ingress? And then even if you do identify this problem, well, you can, okay, route this out. Okay, we're going to change the pin out of the connector. We're going to make this a ground pin. We're going to have guard traces around here. We might even remove some of the solder mask on the traces to actually do that sort of thing. But then it might happen somewhere else. And but you've seen the board here. Like, you know, it's a reasonably complex board. There's just tons of connectors in here. There's just tons of things going everywhere. And well, it's not just about the high voltage backlight. Other issues, other electrical failure modes and other, you know, there's just tons of stuff that can go wrong in here. But this one, with hindsight, seems blindingly obvious. And you could argue, and I wouldn't argue against it, that, yeah, it's a pretty dumb design to put the 50 volt supply right next to this like this. If it was a 3.3 volt backlight or something like that, you know, had a large bunch of parallel LEDs and was just really high current, you wouldn't have had this sort of issue, although you might still get some electrolysis happening between the pins and stuff like that. And yeah, that could ruin your connector, ruin your day, and you might have to clean it up or do whatever, but it's not going to go in and take out your CPU or whatever. What does it do? Did it take out the CPU down here or the MUX chip? Apparently, if you've got one of the designs, it only takes out the MUX chip, which is the MUX, I don't know which chip it is, but it could be like that one or something. And it's a much smaller and simpler chip to actually replace than, say, the CPU over here, the massive big BGA jobby over here. Yeah. And then do you go even further and go, oh, well, we're going to get, look, this connector's here and it's near this joint on the top of the keyboard. And if water goes in here, it's always going to go around. I'm just guessing here from the field. I don't know what a MacBook Pro looks like and assembled. But like water always gets in here. So maybe we should partially conformally coat this board, for example. That's an extra production process. I don't think I've ever seen a conformally coated consumer notebook computer. Maybe they did in those, you know, Panasonic Tough books back in the day or something like. I don't know, but you know, that'd be a drastic over-engineering measure. Or do you add physical routed out slots in your PCB between the pins to prevent, like you could actually do that. You could leave this pad off here and the pad's on the connector. You could actually put a big routing path right through here. So you had no one pin, but you had a big slot. You could have it right down here like this. As a matter of fact, if you just left pins 1 and 2 unconnected, you could have a big massive slot down there and the pin just flaps around in the breeze. It's just happy, you know, it'd be fine just happily sitting above that slot. No worries whatsoever. And then you just get this big, so there's no creepage across your board like that. I'd have to creep over to here. You can see that on this side of the connector, there's nothing over here really that you'd have to worry about. You know, the creepage paths are very large, so you know, maybe they could have done that, for example. That would have been an obvious option. But then they could have done their water ingress testing, for example, and found that, well, water didn't get under these connectors and it could have tested fine and ship it. And maybe it's only 1 in every 10 cases of water ingress where water actually migrates its way into this connector because people like spilled something in there, for example, and it's got the top cover on the connector, and then they went and, you know, stored their notebook upright. They folded it up and, you know, I don't know, shoved it into their bookcase or whatever, or did whatever, stand up vertical, and then the water flowed off the board and then down into the connectors. And does it happen in every single case? So you can't, so you don't know. They could have actually tested this and went, yeah, no worries, that's fine. And in that case, no, you certainly can't blame the engineers at all. So we really don't know unless whoever was on the design team here. But if previous ones, if they actually thought about it, or it was just luck where it actually shunted that power from the backlight to the ground, whether or not they deliberately thought about that or it was just luck of the design and they just didn't think about it in this one at all. But no, there's certainly many cases where I've done designs and we've tested it thoroughly. We have multiple engineers look at it, we do a failure analysis and we figure out all the different ways it can fail, and it still finds some unique way to fail. Or we did actually test that particular thing, but it only fails 1 out of every 10 times. And of course, you're not going to test it 10 times. You're going to, you're doing it a few times, or you know, Murphy's Law. It'll get you every single time. So anyway, it's an interesting discussion about the infinite variability in layout and things going wrong, and whether or not you do failure analysis, whether or not it's good enough, whether or not your mitigation issues are enough, but yeah, this one seems a bit dumb with hindsight. But are they to blame? Are the engineers to blame? Let us know your thoughts down in the comments. So thanks, Lewis, who you subscribe to. I'll link it in at the end of the video. It'll show up there somewhere, Lewis's videos. And let us know what you think about this whole schmozzle that is the Apple product design. And of course, but yeah, Apple really need to lift their game. They're not even off the floor. They need to at least lift them off the floor, out of the gutter, to make products more repairable, and the right to repair bill, which Lewis is involved in, and all sorts of stuff. Very important. And anyway, there's lots of interesting stuff, and we could go deeper down the rabbit hole if you really wanted to, but I think we'll call it quits there. Anyway, hope you enjoyed that video and you found it interesting. If you did, please give it a big thumbs up. As always, discuss down below or over on the EEVblog forum. Catch you next time.